this was the basics of Autosar, and I want to talk about Autosar and functional safety. Yeah, which may be also very interesting to you. So, Autosar provides different functional safety mechanisms like program flow monitoring, timing-related features, communication-related features, end-to-end communication protection, memory partitioning, and every requirement is linked to functional safety requirements. If you're interested in this on this topic, you can visit autosar.org and then visit the technical safety concept of Autosar. There are very good details there. So let's start with communication errors, which are basic in automotive. So as you know, as I said, there are more than 70 electric control units in a car. So these ECUs communicate and exchange data between each other. This exchange of data can affect functional safety. Systematic software errors caused by communication may not only be caused by the hardware of the ECU that sent the message. Yeah, RTE in ECU can also originate from network communication modules such as COM and CAN. And all or part of the message received at the timeout may not be received. So there are different types of communication errors like timeout, like CRC, corrupted message, or repeated message, or delayed message. So they're basically the typical communication errors caused by systematic software or hardware errors, like broken hardware, like systematic software errors. Yeah, and the best known mechanism is end-to-end protection. So Autosar defines 6 configurable end-to-end profiles, and Autosar which are also standardized to detect communication errors. And each profile uses a data protecting mechanism like CRC checksum from CRC library, counter, and a special ID, custom ID. So this is basically a header information contains CRC value and counter information. Yeah. So if the system has more than one ECU, then a special ID can also be provided. The end-to-end profile not only provides protection to the sent safety critical message, but also detects if there is a CRC message counter or timeout error in the received safety critical message. So how does it work? So let's say, let me introduce you the main function end-to-end PO2 protect. So the protect function is used to calculate the CRC of the message to be sent by the ECU and to set the counter value. First, the counter value of the message is increased by 1. So every single message is sent with a counter, and the counter starts with 0, and then it's increased by 1 every time. Yeah. And it is written to the first byte. And the data ID corresponding to this counter is read in the list delivered by the OEM. Using data and data ID, the CRC value is calculated and written to byte 0 of the message. And after the header part of the message is prepared, the message is ready to be transmitted with this header part. So you can see the structure of the transmitted or received data. Basically, this is the data we have. We need to send this or we need to receive this. And if this message is safety critical, then we need to see 1 byte CRC and 4 bits counter. So that we are able to detect if this data is corrupted or not, or if the counter shows us correct information. Let's say if we see 1, and the next time we should see 2. But if we see again 1, then it's a problem. It's a repetition. If we see 3, then it means it's jumping. The control value is jumping from one value to another. Yeah, and CRC detects. With CRC, we are able to detect if this data is corrupted or not. Yeah. So let's jump to the memory errors. In today's complex system software, modular software units often have different functional safety critical levels, like QM, SLA, SLB. And this creates the following problem. Software modules with lower SL level can access and interfere with memory areas of modules with higher SL level. And you can see in the example on the screen, a software module from QM or SLA level can interfere and override the RAM area written by the SLB level software module. This unauthorized write operation can lead to corrupt memory portions and overflow. This situation impairs the functional safety of the software. So, in order to ensure the functional safety of the embedded software, we developed a mechagnome operating system, which creates partitions in the memory, and which prevents the interference of software modules with higher SL rating. In this example, we have partitioned our RAM memory according to the SL degree. We created an OS app. For each part, we have assigned a task to each OS app, and software modules are executed under this task. Thus, memory partitioning does not prevent access violations within the embedded system. So memory partitioning is implemented with our operating system using hardware-level MPU, memory protection unit, or memory management unit. So in short, memory protection unit as a memory protection unit prevents memory corruption by restricting unauthorized writing. This means the low-level software modules can only read but not write. So that we ensure the freedom of the interference. Yeah. There are also different concepts, like partitioning memory can be implemented in different concepts. You see one of them. OS apps are divided into two classes, trusted and non-trusted. So trusted OS apps, also called supervisor mode, and non-trusted OS apps, also called user mode. So in this example, we divide not only the RAM, but the software completely into safe and unsafe areas. Software modules belonging to the safe area can have privileged access everywhere without any restrictions, while the access of the modules belonging to the unsafe area to the memory and the OS is limited. Thus, any code, any software module runs in the non-trusted area cannot affect or change any data in the trusted area. And timing errors. Timing is an important feature of embedded systems. System behavior and reactions at the right time make the system safe. At this point, it's necessary to define the right time. A reaction is expected to occur within a certain time constraint. When configuring Autosar software components at the RTE layer, time constraints must also be defined correctly. If it is not defined correctly, the runtime of a software module is determined incorrectly so that this module can block the other one. So mismatch between software modules. Apart from all this, uh, budget overrun, time limit violation may occur. We expect a software module to complete its work in the time defined for it, not to dominate the OS resources. Any task load on the processor must be monitored and detected. Yeah. Besides that, deadlocks are always problematic for any uh, safety critical system. Let's speak about Watchdog Manager. Watchdog Manager is a core software module of the Autosar architecture. It connects the timer to the corresponding software component. It monitors the runtime of the software component. If any error triggers the corresponding reaction instantly. And Watchdog Manager provides three surveillance mechanisms: live supervision, deadline supervision, and logical supervision. All types of surveillance use checkpoints. That's checkpoints, yeah. They are called checkpoints. By assigning a checkpoint, which has a reporting function to the monitored unit, the watchdog can control the operating frequency of this unit. By assigning multiple control points to the software component with live supervision, different points of the software can be reported. Monitoring and reporting are regular and cyclical. However, live surveillance alone is not enough. That's why time limit monitoring is used along with live monitoring, so deadline supervision. Deadline supervision, on the other hand, is not cyclic but event dependent. This monitoring looks at the transition time difference between two control points in a software component. The resulting value is expected to be higher than the minimum value allowed and lower than the maximum value. There's also logical monitoring, logical supervision, which allows us to check if the software is executed in the defined logical states. Yeah. So Autosar provides Watchdog Manager, which can inform the corresponding software module. Watchdog Manager may enter error code via Diagnostic Event Manager, which triggers error entry in NVRAM or RAM. The Watchdog Manager can also order the respective software module to shut down, and it can trigger the Watchdog hardware to restart the ECU. It can restart hardware and software immediately.